Hi, everybody. We're just going to look at the Unit 1 FRQ progress check. And oh, I've got some goofy things going on here. I don't know what that 3 is doing in there. Okay. Okay, everybody, we're going to look at the progress check for Unit 2 and some of the things that I noticed on there. Here is the very first question. You had to construct the histogram of the distribution of ages. So right away, the first two things that you got to put on your graph are your axes. And whenever you write, as soon as you draw an axis, a pair of axes, before you put the data in, age, frequency. Now a histogram has to have, let me make this screen bigger. Hi, everybody. We're going to go over the Unit 1. Hi, everybody. We're going to go over the Unit 1 progress check and some things that I noticed. And just when I'm going to do I'm not going to do the whole thing. Hi, everybody. I want to go over. Hi, everybody. I want to go over the Unit 1 free response progress check and some of the things that I noticed that we're still having trouble with. Number one, they ask us for histograms. One of the things on our histograms that we're still doing, that some of us are still doing, is we are treating them like bar charts. Whenever you do a histogram, you have a quantitative variable on one. It's quantitative, so that means that you can count. This has got to be a number line. So you can break this number line, just not in the middle of your data, but you can break the quantitative variable number line if you want, 20, 30, 40, 50. Now, and then over here is frequency. You never want to break the frequency axis. Don't break it, because what happens then is it exaggerates the differences between the heights of your bins. This is the issue that I'm taking issue with this one a lot, because people are putting in here, instead of putting a number line, they're making a bin, a bar, and then saying 20 to 30. And then they're making another bar that says 30 to 40. When you do that, that's not a histogram. That's now a bar chart. You're treating it like categorical data. So you have to be a little bit more careful about how you're making that variable axis there. All right. Now this thing ends up, I'm going to give you just kind of a ugly picture of it, but it looks like this essentially. Something like that, okay? So if you remember how that works, if you notice that the frequency is really low in the middle, okay, low in the middle and higher on the two ends. Now, is it symmetrical? It's close enough to symmetrical, okay? The general shape on this half and the general shape on that half is close enough. So if we have to do shape, center, spread, and outliers, the shape this is a symmetrical U-shaped graph. You can't use bimodal in this situation. I let some of it slide, but you can't use bimodal here, because bimodal has to look like a two-humped camel. It has to have a build-up and a fall on both sides. Okay, so it has to be, can't see that. It has to be build up and a fall on both sides. We just have like the back half of them are sheared off. So U-shaped is okay. U-shaped is okay here. Outliers, we can't detect, no outliers detected. So without outliers, centered around 40 to 50 years with a spread of, now, here we go. So the spread, we can use the range, but we got to be careful because we don't know. We know this end is 20 and we know this end is 80, but we don't know where the data is. And we ran into this a couple other times. We can't tell, if we've got a histogram, we can't tell where the actual data is. So we can't say that the range is specifically 60 of approximately 60, or you can say a range of as big as 60, or a range as big as 60, or as small as, well, what if all the data is on the inside of this bar, and on the inside of this bar, then that would be 40. Okay, so we have to be careful in that piece there. And then the last piece says, now a contrast argument, if they say, is it and justify, okay, it is not good enough to say, no, it doesn't look, if it says justify, you just can't say, no, it's not the right shape. Well, you didn't say whether you know what the shape is right. I mean, out of infinitely many shapes in the universe, you got to remember, this is your opportunity to show what you know. It's not an opportunity to just ask the question and be as concise as possible. That's not the goal. The goal is to show as much as you know. So if they ask you about a normal distribution, compare it to a normal distribution or contrast it to a normal distribution, you better darn well show that you know what a normal distribution looks like. Okay? So you would say, in this situation, a complete response would be the normal distribution is bell-shaped and our distribution is U-shaped. So we do not think we have a normal distribution. Okay, it could be that easy, but a lot of you said, no, it's got a U. Well, you don't know. You didn't tell me that you know that this is bell-shaped. Okay, so you got to make sure that you put in, you have to, for a full points there. I mean, partial response was, no, not the right shape. Full response is a strong argument talking about or making sure or calling out the actual shape of the normal distribution. Okay, the goal is not to have a conversation with somebody that knows what's going on in stats. The goal is to demonstrate how much knowledge you have. Number two, this one's great. Okay, almost everybody got the z-score right. Awesome. Okay, part B, we struggled. Okay, some of us struggled. And here's the deal. It says, is it more likely that this type of bird with a weight greater than 13 ounces, so in one distribution, in the north, 13 ounces lived up here with a z-score equal to 1. And in the south, 13 ounces lived down here with a z-score equal to negative 1.2. Now, some of you missed, I think a lot of us missed the fact that it was greater than 13 ounces. Where does greater than 13 ounces live? So how's your justification going to be? This picture is a great justification. You don't like writing? Great, show it. So here we go, boom, boom, boom. We know the probability that a z-score that's greater than 1 is equal to about 0.16. Probability that a z-score is greater than negative 1.2 is about 0.88 if you check them out. So draw those pictures and then you can get it. I think just a lot of people didn't see greater than, or you thought farther away from the center than. A lot of people thought, well, 1.2 is further away from the center than 1, so then this bird's more common in the north. No, greater than. So correct, a 13-ounce bird is more common in the north, but a greater than 13-ounce bird is more common in the south. Okay, so looking at here, now you just have to say a summary statement. Okay, birds in the south are more likely to be greater than 13 ounces. And there's the justification. So the pictures are great. Okay. So in that situation, I know now you couldn't upload a picture in that situation, but at the test you will be able to. You won't have to type that. Okay. If you had to type it, then I would say the probabilities. In the north, 13 has a z-score of 1, and the probability that a z-score is greater than 1 is 0.16. While in the south, the probability of a z-score being greater than negative 1.2 is 0.88. Now you don't even have to really get those numbers, because you know that the probability of a z-score being greater than 1 is less than 50%. Less than 50%. We know that because it's above the mean. Probability of a z-score being greater than negative 1.2 is more than 50% because it's below the mean. So we know 50% of the data, or more than 50% of the data, is to the right. So you could just even make this argument as saying is less than 0.5 and greater than 0.5 because it is greater than the mean because it is less than the mean. So those are the things that I saw that kind of clean up your stuff.